So the integers with addition and the non-zero real numbers with multiplication both form groups. But it turns out you can also see that structure in something like a Rubik's Cube. Welcome to another walk and talk video. Today we're going to be talking about mathematical structures. Now I know the term mathematical structure can maybe seem a little intimidating, but it's actually a beautiful way to look at different ideas in mathematics and how they interrelate. Let's start with some basic ideas. Let's go to elementary school math and see if we can see some patterns that crop up. As you learned in elementary school, there are 4 operations that you typically started working on with integers. You had addition, subtraction, multiplication, and division. Now, if you watch a video of mine about how the order of operations PEMDAS is a lie, you'd learn in that video that it really should be PEMA, because division and subtraction are actually subsets of multiplication and addition. Subtraction, for example, is just addition of a negative number, whereas division is multiplication by a reciprocal. And I'll refer you to that video to see some cool ideas about that. So really, in elementary school arithmetic, you learn about mainly the integers, eventually fractions and decimals. So really it's about the real numbers. And what you learn is that there's 2 operations that operate on the real numbers. There's really addition and multiplication. These operations, addition and multiplication, are what we call binary operations, meaning that they take 2 numbers and produce a number. So they take 2 numbers, do something to them, and produce a number out of it. Now, as you learn about addition and multiplication, and you learn more about it into algebra, you learn that there are some properties that it has. For example, addition has this commutative property, where if I take any 2 numbers and try to add them together, it doesn't matter which order I add them in. So 2 plus 3 and 3 plus 2 both give you 5. It doesn't matter which order I think of them in. It doesn't matter if I start at 2 and count 3 up to get to 5, or if I start at 3 and count 2 up to get to 5. It'll produce the same number. So this property that it doesn't matter which one you start with is called the commutative property. There's other properties too. One that is maybe the least appreciated is the associative property. What happens if you want to add 3 numbers? So like 2 plus 3 plus 5. The problem with that is that the operation is only defined on 2 numbers. So if you want to be able to add 3 of them together, you have to have some way of translating what that means into the 2 number at a time situation. This is where the associative property comes in. The associative property tells me that it doesn't matter if I add the 2 and the 3 first and then add the 5, or if I add the 3 and the 5 first and then add the 2. In fact, if I couple this with the commutative property we had before, I can also add the 5 and the 2 first and then add the 3, and I get to the same place as well. So these properties really are indicating things that we already know about the real numbers, that it's intuitive that you should be able to rearrange these. I mean, if you think of these numbers as being represented by stacks of rocks or pebbles or something, if you turn it into something real like that, where you have, a pile of 2 stones, 3 stones, and 5 stones, it doesn't really matter how you merge those stones together to find out that you have a total of 10 stones. You can put the 5 and 3 pile together and then to the 2. You put the 2 and the 3 pile together and then put the 5 pile. In that case, you can kind of just mush them all together. And what these properties are saying is that how we add is actually independent of which of those methods we try to use. The associative property makes us feel like it may not be really important to say because it feels so intuitive. But if you didn't have the associative property, arithmetic would be remarkably hard. You'd have to put parentheses in all the time to tell us which 2 operations have to go first. The fact that it doesn't matter makes a humongous difference in the ease with which we can describe what's going on. Another important property of addition is the fact that there is mathematicians will call it an additive identity. I sometimes like to think of it as an additive nothing. This is the number that does nothing when you use addition with it. This is the number 0. If I add 0 to any number, it doesn't do anything. So 7 plus 0 is 7. 15 plus 0 is 15. The adding the 0 doesn't do anything to it. And it's referred to as the identity in mathematics because it's kind of giving back the same thing that you put in, sort of like checking your ID or something. But I think I like the idea of thinking of it as a nothing instead of a identity, because it kind of hints at these ideas a little more of how it behaves. The last property that we want to talk about in addition is that every number has what's called an inverse, an additive inverse. What this is it's a number, you can think of it as a number that undoes another number via addition. So if I want to undo, in some sense, the number 6, I want to undo it, meaning I want to move away from the 6 and go back to the nothing, right? So this is the number that I would have to add to 6 that would get me back to the nothing. That number is negative 6. 6 plus negative 6 produces 0, the additive nothing. So the negative 6 inverted the 6, and when I add them together, it gets me back to the nothing. We have 4 properties now: commutative property, associative property, additive nothing, and additive inverses. It turns out that multiplication has similar properties. There's a commutative property of multiplication. If you take 2 times 3 and multiply it together, you get 6, and that's the same as if you do 3 times 2. This one is even cooler to see in terms of like a practical application, because you can think of multiplication as giving you the area of a region. Or if you want, it gives you, if you have a bunch of squares put together in a rectangle, you can find the total number of squares in a rectangle by taking the number of rows of squares and multiplying it by the number of columns of squares. So a 2 by 3 rectangle of these little squares would have 2 rows and 3 columns. So you can either think of how many do I have if I have 2 rows of 3 columns each, and that would be 2 times 3, or I can think of it as 3 columns of 2 rows each, and that would be 3 times 2. So in other words, we can think of it as 2 groupings of 3 or 3 groupings of 2. And either way you do that produces the number 6. That's why multiplication is commutative. And that's what it's trying to say, is that it doesn't matter which way you think about it. And the real numbers have this property. The multiplication in the real numbers, like addition, is also a binary operation. So it has the same trouble with trying to do multiplication of 3 numbers, just like we had the issue with adding 3 numbers. So when you multiply 3 numbers together, you have to use this associative property that multiplication also has. So if I have 5 times 2 times 3, it doesn't matter if I do 5 times 2 first and then multiply by the 3, or if I do 2 times 3 first and then multiply by the 5. Similar to the addition issue, if I couple this with the commutative property, it also doesn't matter if I do 3 times 5 first and then multiply by the 2. So it behaves the same way as the addition. Well, it turns out that there's also a multiplicative nothing. This is a number that doesn't do anything when you multiply by it. Can you think of what the multiplicative nothing in the real numbers might be? If you said the number 1, you're right. Because if we multiply anything by 1, it doesn't do anything. 3 times 1 is 3. 5 times 1 is 5. 29 times 1 is 29. So that 1 doesn't do anything multiplicatively. So it's the multiplicative nothing. This also helps us understand how to find multiplicative inverses. In this case, we want to find a number that when we multiply it by another number, it gets back to the multiplicative nothing. See, that's the same structure as what we did with the additive nothing and additive inverses. So if I have the number 5 and I want to get back to the multiplicative nothing 1 using multiplication, what number would I have to multiply 5 by to get to 1? And now you can see why the algebra becomes important in this case here, because that's actually solving the equation 5 times x equals 1 for x. Algebra ends up playing a huge role in trying to understand these different structures, but that's a discussion for another time. Let's just get back to the structure itself. 5 times some number equals 1. The number has got to be 1/5. 5 times 1/5 would give you 5/5, which is 1. The 1/5 is kind of easy to grab from the 5. If you think of 5 as being a fraction over 1, right? So it's like 5 wholes, 5 over 1. The inverse, multiplicative inverse, is just its reciprocal. You just flip the fraction upside down. That's what we mean by reciprocal. And that's the multiplicative inverse. And this works for any number. If you have 3 halves, for example, its reciprocal is 2/3. Half of 2/3 is 1/3. And if you had 3 of those, you'd get to 1. So 3 halves of 2/3 is 1. Now we see something really fascinating about this. Because what we just observed is that the underlying structure of addition with the real numbers matches the underlying structure of multiplication in the real numbers. It has all the same properties. And this might make you wonder if there are other things that have similar behavior. This brings us to one of the big ideas in mathematics. And I wish we taught this at a younger age, because I think it would help us understand better what math is for and how useful it can be. But for some reason, our K through 12 system is designed purely to get people to calculus as fast as possible by whatever means necessary. As a result, we end up focusing only on a bunch of algorithms and algorithmical thinking. I've got this problem, so I use this formula and I plug and chug. And we miss the structure, we miss the beauty, we miss the thinking like a mathematician or thinking mathematically. And really, that's what's the most valuable part about learning math, is to gain that ability to think mathematically. Anyway, the structure of multiplication and the real numbers is almost exactly the same as the structure for addition. And so this brings us to a new concept, which is the idea of abstraction. What we're going to do is we're going to move away from the concrete notion of the real numbers, where we have like nice examples of things like pebbles that we're adding together, or rows and columns of things and trying to find how many total squares we have. Those are very concrete notions that we understand. But we're noticing that some of the behavior of the concrete notion of finding how many squares you have in a rectangle matches some of the behavior of simply putting a bunch of rocks together too. That's what we noticed when we saw that they have the same properties, is that there's something about that structure that's true in both places. Well, if we could understand something about just the structure itself without attaching it to the concrete idea, and say we could find something out that's true about just what that structure is, well, whatever fact we found would be true in both places, because both places share that structure. And we made a comment about the structure, not about the example. This is the idea of abstraction. If we can identify the same behaviors in 2 different concrete ideas, we can instead look at the behaviors themselves and study that on its own. And any facts we find out about that behavior is then true in every set of examples that exhibits that same behavior. So let's talk about a simple one. Instead of using 2 operations, let's just use 1. Let's think about the integers with addition. These guys have those 4 properties that we mentioned. That is commutative, that it's associative, and that it has an additive identity and additive inverses. And one other subtle one that we also want to make sure we do, that automatically happens with integers, but we want to make sure it happens in these other ways if we're going to talk about abstract structures. And that's the idea that if I add 2 integers together, I get another integer. So I want to stay sort of closed in the type of objects I'm talking about. So that structure there actually occurs in many other places. For example, the same kind of behavior of those 5 properties now happens both with integers and addition, and also non-zero real numbers with multiplication. So both of those objects, those non-zero real numbers with multiplication and the integers with addition, both share these same 5 properties. So if we wanted to understand just the behavior of those 5 properties and prove something about that, we would know that that fact is true both in the integers with addition and the non-zero real numbers with multiplication. It's kind of like a buy one, get one free kind of thing, or buy one, get a bunch free. If you show that this is true abstractly, then it's true everywhere. So let's peel those properties off and abstractify. What I mean by abstractify is let's remove the concrete example from it. So instead of addition and the integers, or the non-zero real numbers and multiplication, what we're really going to have is a collection of objects instead of numbers. We could still call the objects numbers, but you don't have to. Usually in mathematics, we refer to them as elements. So you get these elements and you have an operation on those elements. That operation has to be a binary one. So it has to take two elements and produce another element which satisfies the first property of closure. Now, if we also require that that operation has those other four properties, the commutative property, associative property, additive nothing, or rather an operational nothing, right? Because it was an additive nothing in the integers, it was a multiplicative nothing with the non-zero real numbers. We refer to this in mathematics, like I said before, as an identity. So we'll say it has to have an identity element, which is the operational nothing. And then we also have to have inverse elements. Every element has to have an inverse. So if it has those 5 properties, it's a type of structure that we refer to as an abelian group. Now, it has an adjective in front of it, which might make you wonder, well, what's a group? Well, it turns out that there's a lot of structures that are commutative out there, but there's also a lot of structures that have all of those properties except commutativity. So 2 times 3 equals 3 times 2. Not every operation has that property. So if we remove commutativity from our list, so that all we have now is closure. You do the operation on any 2 elements, you get an element. Associativity, if you have 3 elements that you're trying to do the operation on, it doesn't matter which 2 you do first. An operational nothing, or an identity element, and you have to have operational inverses. Every element has to have another element that when you do the operation on those 2 things, you get back to the identity element. Those 4 properties together form what we call in mathematics a group. So the integers with addition and the non-zero real numbers with multiplication both form groups. But it turns out you can also see that structure in something like a Rubik's Cube. So a Rubik's Cube has a group structure as well, where instead of numbers, the elements are the different moves that you can make. So rotating like the side, that's a move. That move is an element in this space. The identity element, by the way, is no move. And the operation, the addition, is simply stacking the moves together. So if I do left and then top, that's an addition. This is an example of a non-commutative operation, because if I do left and then I do up, that produces a different cube than if I do the up first and then do the left. Notice that is a different position for the cube. So if I do them in the opposite order, it does not stay the same. You will notice though that it has inverses, because if I do this rotation here, which you could think of as a left move 1 position, I can also do a left move -1, which goes back the other way, and that produces the same thing as before. So those of you that are out there that do Rubik's Cubes, typically the way people solve Rubik's Cubes is they use a set of algorithms to get it back to the identity. And these algorithms are basically different sequences of moves that do certain things on the cube that eventually get it back to the solved state. And those that solve Rubik's Cubes know that these algorithms are typically listed as a sequence of moves that you have to do in a row. Well, what you're doing in that algebraically in the structure is those moves, remember, are the elements in there. And so you're adding them together by stacking them on top of each other. So what you're really doing when you do an algorithm on a Rubik's Cube is you're doing a sequence of moves to add to the state that it's at. The goal could be phrased then as trying to find the inverse of the state that you're in. So when you take a solved cube and you mix it up, you do a sequence of different moves, and usually you don't pay attention to what they are because you're trying to make it a mystery. But you do a sequence of moves to get it into a unsolved state. Now, if you kept track of those moves precisely, it's actually really easy to undo. You simply do those same moves in reverse order backwards, and that'll get you back to the solved state. The problem is that you don't keep track of those moves. So that solution is typically not available. So instead, solving the Rubik's Cube is about trying to find an algorithmic way to generate a number in that system that is equivalent to the inverse of the moves that got it into that state in the first place. Now, the Rubik's Cube idea is all well and good, but really the real beauty and power of this is the fact that we recognized that there was the same structure in the integers as in the Rubik's Cube. So when we find out facts that are true about elements and an operation that obey those properties, those facts are true both with the integers and on a Rubik's Cube, where the numbers or elements are the different moves and the addition is stacking them together. So what we found here is two really powerful ideas. The first is that mathematical structure can exist in a lot of different places. Sometimes very unfamiliar ones can actually turn out to be similar in structure to things that are very familiar. The Rubik's Cube probably feels pretty unfamiliar to most of you, but the integers probably feel very familiar. We do arithmetic with them all the time. So the fact that they have similar structure is a powerful idea to help us relate those two ideas together. The second powerful idea is that this type of abstraction helps us realize that we can understand the Rubik's Cube, or whatever other example you're using the language of the structure. Because we can describe all this behavior well with talking about the fact that the Rubik's Cube is a group, a lot of these cool facts that are true about Rubik's Cube, like for example, the fact that there is an optimal algorithm to get back to the identity state. These are facts that are proved using the mathematical way of talking about the Rubik's Cube. The fact that we are able to prove that there is a sort of God algorithm is a group theory fact about the Rubik's Cube. The last thing that I want to point out is just how many places actually depend upon the ideas of groups. What keeps your bank account secure online uses what's called modular arithmetic, which is partly related to the group structure of modular arithmetic numbers. It's particularly modding out by a very large prime number. It's an algebraic structure that we understand because we talk about the mathematical structure itself. We recognize that that behavior is somewhere else, and we were able to find a place where the arithmetic to solve something is so remarkably complicated that it's practically impossible for computers to break it in most ways. And we come up with better ways of doing this all the time. This is the RSA scheme. There's tons of groups in understanding physics and data science. And there are other algebraic structures too that are incredibly important. We talked about groups, but there's also rings, which is what you get when you do both multiplication and addition. You can get things like vector spaces. The vector spaces, for example, they're a form of a group that has an extra operation called scalar multiplication. It's the algebraic structure that data follows. So if you want to understand how data works in data science, you have to understand how that underlying mathematical structure functions. This is what mathematicians actually refer to when they talk about studying algebra. Algebra to a mathematician is understanding structure. Thanks for watching a Scholar Sauce Walk and Talk video. Well, I almost just tripped on that thing there. And if you're interested in this kind of content, we have many other videos on Scholar Sauce. You should check them out. Don't forget to like and subscribe. We'll catch you next time. What's purple and commutes? An abelian grape.